Good evening, everyone, to this last session of this Dive into Deep Learning series. As you can see on this first slide, today we're going to talk about a very interesting topic, namely generative adversarial networks. Those networks are really interesting, and as I will show later on, they really have revolutionized basically the synthesis of images or sound and so on. And today we're going to try to understand how these networks are built. And this is the current sessions plan. And as I've already said previously, tonight's going to be the last session of our sessions. And today we're going to talk about generative adversarial networks. So let's jump straight into the theory, and let's think a little bit about the motivation, because so far in those sessions, we have mainly discussed what are called we have done discriminative learning. And what we mean by that is that given some input data that we have, we try to obtain a prediction. So it could be a class, or it could be some real valued property, for example, of a molecule, or just a value in general. And what it really means is that we're trying to learn a conditional probability distribution. So what is the probability of getting class or a value y given some input data? So this is how we would write this. But today we are especially interested in generative modeling. And it's a little bit different because what we're trying to do here is to capture either the original distribution, so how is the input data distributed, or how is the input data distributed with the with the associated labels. So we either try to model P of X or P XY. And you might rightfully ask, why would we want to do that in the first place? And the short answer to that is that we can generate new data samples resembling the initial distribution. And here I'm showing two very impressive examples of GANs, so the generative adversarial networks that we are going to discuss today. And if you don't know about those websites yet, they're really great. It's called This Person Does Not Exist. And this picture you see here is a picture which was generated from such a GAN. So this person really doesn't exist. It's a novel image. And there is, funnily enough, also this cat does not exist, which was trained on cat images. And here you see a cat which, of course, there are probably cats which resemble it, but this specific cat here doesn't really exist, so to speak. So the motivation, again, is to try to generate data samples which resemble the initial distribution, but training a generative model is a harder task than the training a discriminative model. And here I'm mainly going to follow the Google Developers GAN course, which is really great, and also one resource I highly recommend, where they nicely explain how GANs work. Sorry, but in this course, what they are basically saying is that discriminative models try to draw some boundaries in the data space. This is shown here in the figure on the left. So here we have a discriminative model, and we try to learn this conditional probability distribution. So our model is going to try to put a line between the points here. And the model really only needs to put a line. And even if it's a little bit off, it doesn't really matter. It still will be okay for whatever downstream tasks we want the model for. But the point is here, laying a line is considered easy. But generative models, they have to model how the data is placed throughout the space. So you can see it here on the right side, where we are trying to model the joint probability distribution. And here, the model really needs to understand all of the space. So it can't just put a line. It really needs to know where each data point is placed in the space to be useful to us. But the good news is that the GAN framework really allows us to learn very powerful generative models, as we will see. The architecture of GAN models or of the GAN framework is quite simple, to be honest, because there are really only two major components to it. The first one is a generator, which needs to generate or propose new plausible data points. It's the one here on the left in red. And we also have a discriminator, which needs to tell us if the data provided to it, if it comes from the generator or if it's real images. And we will later see how it plays together. But these two components are all you basically need to have a GAN framework. So here's the ideal scenario. First, of course, our model won't be good, but let's imagine that our discriminator is already well trained and he can recognize whether or not a bill is fake or real. So the generator will first try to render a bill, but obviously it won't be good at it because it's not trained yet. And the discriminator can tell, okay, the one on the left is for sure fake, but the one on the right seems like a legit bill. And as the training goes on, the generator will actually become better and better at generating bills. So here, for example, you can see it recognized that it has to put a number on the top left, and it also probably should put a face somewhere on the bill. But the discriminator still can tell, okay, this bill still looks fake enough, so I'm gonna reject it. But if we keep doing that long enough, the generator will be able to generate a bill which just looks like the real deal. And the discriminator won't be able to tell whether or not the generated data comes from the real data distribution or the real images, or if it was generated by the generator. So the discriminator really has two sources of training data. So the one comes from the distribution that we want to learn, so the real images, for example. And we're just going to sample some images here and feed it to the discriminator. And also samples generated by the generator. And how we're going to train the discriminator is just to penalize it whenever it misclassifies the real instances as fake ones, or if it misclassifies the fake instances as real ones, because we want it to tell us which ones are fake and which ones are real. For the generator, what we have to do is first sample some random input, feed it to the generator, and the generator should give us an image, for example. And these images are then passed to a fixed discriminator, and I will explain why that is. And we then calculate the generator loss, depending on whether or not the discriminator was able to see that it was a fake image or if it was a real one. But here as well, we are going to train the generator by back propagation. However, here, as you can see, if we look at the data stream, we go from the random input all the way through the generator, but we also have to go through the discriminator here. So how should we train this system? It's a little bit hard because we have to do two things at the same time, right? So we have to train the discriminator, which needs to distinguish the images, but we also need to train the generator, which needs to generate new samples for us. So the idea is that we are actually gonna fix one of these two and then train the other one. And every n epoch, we're gonna switch between these two. So what we're gonna do is first train the discriminator and keep the generator fixed for a certain amount of epochs. And then we're gonna switch. So we're gonna train the generator and keep the discriminator fixed. And this balancing of training these two models one after each other allows us to train the overall GAN framework. However, there are some convergence issues, and it's not very difficult to imagine why. Because as the generator gets better at creating fake samples, the discriminator cannot really tell us whether or not it's real or fake. So it only has a 50% chance of being correct every time, right? So the feedback that we are going to get from the discriminator becomes less and less useful over time. And because this information is not useful or might even be junk information, the generator might be trained on data which is useless and then later collapse due to this nonsense information. So GANs really suffer from these convergence issues. Let's talk a little bit about the loss function. It was originally proposed, the one proposed in the original paper is called Minimax Loss, and it's quite easy to understand, so we are just going to walk through it. So here is the whole equation. But if we take a little bit of a closer look at it, we can see that the first term, it just penalizes the discriminator for not recognizing the real data samples because here, if it's wrong, the log uh, will be very low. And in this case, this whole term here will be also low. So we're trying, sorry, this term here is going to be big. So we're trying to minimize this. And the second term basically penalizes the whole framework for labeling fake samples from the generator as real. So this is the sample G of Z, where Z is the noise, is the generated samples, which is passed to the discriminator D, and it's 1 minus the log of that. But here easy is just means that we're here looking at the samples generated from the generator itself. And one thing to note is that because when we train the generator, uh, so if we look at the first term, we see that there is no big G involved in this term. And what it means is that the generator here doesn't really come into play. So it shouldn't, the loss for the generator shouldn't depend on this term here specifically because it doesn't make sense. So when we train the generator, we are only going to train on the second term here. But when we use the discriminator, we're going to use both terms. And there are two, or actually three very common issues with GANs. The first one is the issue of vanishing gradients that I think we talked about in one of the first few sessions. And this can happen if the discriminator is too powerful from the beginning, because then the information cannot really flow back to the generator. And the proposed solutions is to use a modified min-max loss function or the Wasserstein loss. But unfortunately, I'm not very familiar with these, so I'm just gonna leave it as it is for now. The second issue that usually arises is called mode collapse. And to explain it, let's just take a step back and think about why we want to train GANs. So the idea here is really to have at the end a generator which can produce a wide range of different outputs for us. But it's possible that the generator finds a very specific region of the data and starts to exploit it where the discriminator cannot classify correctly. And if this happens, and if the discriminator cannot learn and is stuck in this local optimum, the whole system basically gets trapped and cannot progress because the generator is just going to propose data samples which trick the discriminator. And we don't really want to do that because we're not interested in few solutions, but we really want to have a generator which can produce a wide range of different outputs. So here the solutions is again to either use this Wasserstein loss, or another idea is to use unrolled GANs. And from what I understood is that unrolled GANs, or in unrolled GANs, what we do is we also use future discriminators as well, because we don't want the generator to over optimize on the current discriminator. So by using several discriminators, we make sure that we don't get stuck in this trap. And with this, I'm already finished with the theory part. I'm sorry it's a little bit early, but I can give the mic to Mritunjay.
So yeah, basically now we are going to code or implement DCGAN essentially. So like DC stands for deep convolutional GANs. So here we are essentially going to use convolutional neural networks in order to generate Pokemons essentially, right? So this has always been my fantasy, and now it came to reality. So yeah, I'm pretty happy about that. So as Pierre mentioned earlier, so basically this is the entire gist of GANs. Essentially, here instead of using fully connected networks, we are going to use convolutional neural networks. Um, Now, so since we are going to be implementing it, so I think it makes more sense to describe this. So uh, while implementing, we are just going to give the generator some noise vector essentially, or an n-dimensional noise vector. From that, the generator is tries to create Pokemon to the best of his ability, and from that, discriminator tries to say whether it's a real Pokemon or it's a fake Pokemon from the generator essentially. So that is the entire idea behind this image. So if you move forward, so this image is taken from the original DCGAN paper. So as you can see, it's a bit more convoluted or it's a bit more involved in this case. And the reason for that is because like we have multiple layers of deconvolution and convolution. I will talk more about what exactly is deconvolution as we move on. But at a high level, this is what DCGAN essentially looks like. Uh, for this, we are going to use Pokemon DB as our database, and then we will do some transformation in order to make it good enough so that discriminator can use these images essentially. Um, I guess with that, uh, this is the entire preprocessing step. So without further ado, let's try to implement this preprocessing step before moving forward and try to create generators and discriminate. Also, at any point of time, if you feel like my voice is quite low, so feel free to let me know. Because sometimes I speak very slowly. Yes. Now with that, I'm just going to initialize my notebook, and just like always, we are just going to install the DTL library because it has a lot of really nice classes, functions that comes in handy uh, while implementing a DC. Yeah. And then we are just going to import it, and then with that, let me download the document itself. Now, finally, we are going to just pre-process our data essentially. Now for pre-processing step, what exactly we are going to do? So we are just going to take all of the images coming from Pokemon dataset, and then we first going to resize to 64 by 64 essentially. Uh, then we will rescale the value between -1 and 1, and the reason for that is because the generator uses TANH activation at the end of the generator block essentially. So the the range of TANH activation is essentially -1 and 1. So since we are going to be comparing the images that is being generated from the generator as well as the original image, we wanted to keep it in the exact same set or in exact same space, uh, if that makes sense. Now with that, let's implement this. I'm just going to take the batch size to 256 and over equal to torch. Yeah, also Torch Vision has a really nice collection of utilities that we can use to uh, do the transformation process. So it's kind of like an ETL, but a primitive version of ETL, I would say. Transforms results. Let me close this one because it's annoying. Yeah, so the property of two tensor is that it essentially maps the inputs between 0 and 1, essentially. So now your range is from 0 to 2. Previously, it was 0 to 255 because it was pixel values. Now it is going to be 0 and 1. But since we want it between -1 and 1, essentially, we are going to be normalizing it with mean equals to zero point 0.5 and the standard deviation equals to zero point 0.5. This essentially takes our entire data between -1 and 1. With that, our transformation process is completed. Now, just like in the previous session, we are going to be initializing the data iteration, uh, which is just a data loader. So yes, that's it. Now, with that, let's visualize our images. Data iteration. Also, so does anybody else have any suggestion? It works for me. Well, that is quite interesting. I'm not sure what's the problem, so I'm going to go down to tools, add interesting, and see if it works. Okay. I wasn't sure what's the problem. Let's move on. Because we are always short on time, essentially. So with that, we have all of these images, uh, and as you can see, these all are Pokemons. And our objective is to essentially create these Pokemon using a generator and using, of course, DCGANs. Now, as I mentioned earlier, this is the entire architecture, and I have also added the helping uh, sheets with each and every one of the stages that we are having inside a particular inside this architecture essentially. So as you can see, the inputs is going to be batch size, and in this case, I am using a 100-dimensional noise vector, and hopefully I want the number of channels as 3 because of course we are using RGBs. It's going to be a colored image, and then the width and height is going to be 64, and since it is the generated output, and of course it is identical to our real images. Once we have both of them, we can put it inside discriminator and we get a score out of it, and from that we can essentially train generator and discriminator in the same way that we have mentioned uh, in the theory part essentially. So if we dive deeper into generators, so it consists of 3 different components, right? Uh, and these all are G block. I will talk more about it, and deconvolution and tanh activation function. So G block essentially consists of 3 things. This is just a deconvolution plus a batch norm and then relay activation. Now, what exactly is deconvolution? So it's kind of is a mirror image of convolution. In that, in the case of convolution, we are actually reducing the dimensionality, but in the case of deconvolution, we can kind of increase the dimensionality. So from 3 by 3 inputs, we can have 5 by 5 inputs using all of these 2 strides and panel one, for example. Now, with that, Of course, as I mentioned earlier, this is deconvolution there, and then we have time separation. Now, of course, as we've done in the previous session, these are the shapes. So this is the input shape and this is the output shape. If we look deeper into each and every output of G blocks and all of the other blocks, what we find is that we first are going to take that 100 vector and kind of project it using G blocks and project it into 64 by 8 and 64 by 4 and by 2 and then 64 at the end. The advantages of this, of course, you can put it to any number of different channels essentially. But the basic idea is that we want it to have as much capacity as we want to see, right? And since we are using deconvolution, we are actually able to increase the width and height incrementally until we get the desired width and height, which is 64 by 64. With that, let's implement this. Now, the G block part, as I mentioned earlier, is going to take these arguments. First is the output channel, and then it has keyword arguments, which is input channels and kernel size and stride and padding. Now, using all of these, we can essentially define our G block, which is contour transpose. Of course, as I forgot to mention, deconvolution is also known as convolution transpose. So we can use that convolution transpose package that comes with PyTorch, which really helps us to implement it so we don't have to do that from scratch. Output channel is only with output channel and kernel size, bias equals to, right? And, and as I mentioned earlier, we are using railway activation function in the G block. Just let me remove this pass because we are implementing it. Concept of activation. And the forward pass, this is what really happens. We are essentially going to chain all of the things that we have defined previously. Point to the transpose and x7 input. So just let me check. So we can do function, kernel size, padding, biases, both activation, rationalization, and control tasks. And present, let's see what's it doing.
Mrityunjay,
Hmm.
if you go to the class definition of the generator, maybe you have to call super, the super method.
Oh, sorry, I totally missed it. Yeah, this is something I implemented it, but I haven't. So thank you so much for that. And it's working. Thank you so much, dear. Uh, and of course, now we have to implement our generator using the G block. So if we look deeper into it, now that we have already defined the G block, deepen is already being implemented by developers at PyTorch and as well as standard solution manufacturers. So we are just going to sequentially couple each and every one of them and create a generator block. Now, and sequential, I'm sure you've seen it earlier. And just like before, we are just going to take 64 by 8 for the first layer, essentially. We are just going to take this stride equals to 1 and then the drill is exactly the same. So I'm just going to put this 4 times, I think. Right. Now the input channel is going to be this, and the output 2 by 2 and P is this. And yeah, of course, we don't need silent pattern because we are just going to use the default. And just to check, we are using this as an input, and we are putting this as an output, this as an input, and maybe go just to check. Right. Hopefully, it should. I don't know. I don't want to jinx it right now. Transpose the 2D, where the input channels are going to be just the NG, right? And the output channels are going to be R3, right? Because of yeah, the uh, channels which is RGB, the current side is going to be now finally in our last layer we are going to be using damage application. Okay. They should hopefully give us what space, and lo and behold it works because I haven't jinxed it this time. Now with that we have a generator and now we can try to implement the discriminator part, right? So discriminator is just going to be the reflection of or the mirror image of the generative part, right? So more specifically, in this case, we are only using two different components. One is the D block and another one is conf2D, right? Now, in the D block, we are using conf2D instead of deconvolution, right? Because now we have to project everything in a single value, and from that we are going to be judging whether both of these network are doing right or wrong, or good or bad, essentially, using, of course, zero sum game. And using that, we are just going to back propagate it and eventually learn learn to generate these Pokemons, hopefully, right? So with that, okay, so let me talk a little bit more about debug. So we have a conf2D, and then from that we are just going to put it inside a batch mount in there, and finally a leaky value. And for the conf2D, we are just going to use the vanilla conf2D. So for those who've seen leaky value for the first time, so basically it's just this curve essentially. So what do I mean by that? It means that the negative side, uh, the negative definite region of this coordinate space is going to give you negative values, right? Instead of zero. So in a classical value, it's zero in the left side and x in the right side, right? But in the case of leaky value, it's going to look something like that. Now with that, of course, following the previous trend, we have these input shapes. As you can see, we have already transformed our inputs to 64 by 64 and all of the values between -1 and 1 with the three input channels, which is RGB, and we wanted to get out of this discriminator a single value through which we can actually optimize and train both of our generator and discriminator. Now, of course, if we unwrap the discriminator, each and every one of the layers of D block looks something like this. So the output of the first D block is going to be 64 channels and 32 by 32 image essentially. And just following the previous trend, we 64 by 2, 64 by 4, and 64 by 8. So this is what I mean by mirror image of the generator part, because like previously we are using 64 by 8 and then extrapolating it and in some sense, and now we are uh, doing subsampling. Previously we were doing super sampling, right, or upsampling, right? Now here are the outputs, and this is the final output after the conf2D. So without further ado, let's implement this. So where am I? And here, and yeah, of course, the mandatory let's code slide essentially. So using the D block, of course, as we've done previously, we are first going to be implementing the D block. So let's do that. And this time I should remember initializing the super class. The block self and initializing it with elements. And 2D is equals to any dot in channels is just the arguments. drives, and that bias is going to be false. Again, that's because that's if I'm able to type, that's and this is the output channel as the argument in the touch now there. And finally, we have the activation, which is leaky ReLU instead of ReLU. And it requires alpha as a hyperparameter. So that activation, let's define our forward pass, which is just the composition of all of those years that we have defined earlier. And then circle 1, 2, and the inputs of 1 to 2 is which is our input, right? And in the D block, the input is now going to be the generated image as well as the real image, right? Because it's essentially is a classic one. Effects on this. Hopefully it works. And it does. Now let's implement our discriminator method using all of those D blocks and the count to the in the end. So we are going to be using the sequential which take these which takes these arguments, which is essentially just the first folio is going to be the D block, right? And then we are just going to be using count to the in channels it's going to be ND, right? Number of dimensions, and the output channels is going to be now. So if we go back, we can see that we want the okay. So we have already defined this. We have to define this one. So now we are just going to be multiplying it by 2, and then 4, and then give it image. So MD by 2. And finally, this is going to be a last D block link. Whose output is going to be 64 by 8. Channels is equals to by 8. Right? As let me check. Here it is. Then we this is the input channel. Yeah, makes sense. And final layer of the discriminant. Output channels is going to be 1 because this is just a similar value that we are going to be using. in our final objective function by superscript. Right, right. Okay, finally we have a similar value which is exactly what we wanted. With that, we finally comes down to training our neural networks. So as mentioned earlier by Pierre and his great slides in the theory part, we are just going to be updating the generator and discriminator using kind of like a zero sum game, right? Uh, let's implement this. So first we are just going to be defining how are we going to update the discriminator, and then we will eventually define how are we going to update the generator part. So for that, first let's put this into a memory separately. And then, so okay, so let me do that. And so, yeah, so I'm using this part. So as you can see, now if this value is going to become 0, then we will eventually going to be updating the discriminator. Otherwise, we're going to be updating the discriminator as well as the generator, as mentioned by Pierre earlier. So I'm just going to define once as all of the real images as 1, right, and all of the fake images as 0. So we're just going to take the back size. And of course, it is important to add devices, right? Because since we are using the GPU, so we have to utilize it to the best of its as best as we can. Right? Zero is just going to be back size. Device is equals to so we will eventually be defining the trainer D in the in this function essentially. So if we if nearby is going to be of Z. Yeah, makes sense. Now, of course, since you don't want it to compute the gradient for the discriminator, right, while updating the the sorry, we don't want to compute the gradient for the generator while updating the discriminator part. So I'm just going to detach it. Detach. Detach. Yes. I feel like we should be adding some elevator music while this kind of doing.
Nah,
Uh,
it's fine.
yeah, yes, thank you. Like, yeah, like keep saying something. I don't know. So as I mentioned earlier, we are going to be assigning zeros to the fake wise and ones to real wise. Mm, And I have a feeling that, okay, so basically I have this back and post this, and I have completed my entire loss and this completed two because it will act nicely when I'm grading the propagation. Loss T, and I'm just going to initiate that train of the stepping up person is going to step it, which will eventually update the gradients in the distributor, which is exactly what we need. And that let's update our generative part, right? Uh, and I should also comment something on the trainer, which is over, and just like the real life is the outputs of the real images and with is equals to the with x is equals to the outputs of the generator, right? And which will eventually give me fake y. Right? So I'm just going to put it inside here, um, and then just defining the loss here, and then just following the backward pass, and eventually updating the gradients in the discriminator. I hope that makes sense. Now let's define a generator, which is just going to be the same drill. Not the same drill, but for the first few lines, I guess. And once is going to be so we should be just copying the this whatever trainer to take. So this is just going to be take images, right? And we can take profile. Going to be the discriminator by taking this take. And with that, let me kind of compartmentalize it. I really wanted to make it a bit more modular, but it's just for learning purpose. Yeah, so once I have fake device as well, I'm just going to define the loss, right? Or loss has already been defined in the training part. I'm just going to give them some arguments that means essentially. Of course, it looks kind of blinding right now, but it will all make sense once we will to define the main training loop. So I have this one, and once since Yeah, of course. It's going to be the other way around when we are defining the, and when we are updating the generator loss. G dot initializing the backward pass and then getting all the gradients in the generator part that will finish our definition of updating the generator. Now finally, we okay. So how are we? Okay, so we have 20 minutes if I'm not wrong, right? So now in the main training loop, I'm just going to define the training. The loss, right? Essentially. Okay, so for this one, let's use the binary cross entropy with logics uh, as the loss, right? And that is the reason why we think this, because this is going to be the logics in the binary cross entropy. Now, I think this must be familiar because we've already seen it earlier. So we're just going to be initializing uh, weights of both the generator as well as the discriminator with the following which is the 0 mean and this 0.02 standard deviation. W and the G parameters. With that, let's initialize the network, both of the networks, which is generator as well as the discriminator. To device, yeah, of course, we wanted to utilize our GPUs essentially. So that is the reason why we have to insert this here. Device. Device. Oh yeah. So now for training, we have two hyperparameters. First is learning rate, and another one is beta. So beta is for Adam optimizers. Requires us to. I think it's the momentum parameter. I'm not sure. Scalar b is equals to dot thing. I hope open works. Yeah. Um, Trainer hyperparameter as to I don't know. net generator. Sorry. So we can check the inputs, parameters, and we can do Taylor discriminator generator. Now I'm just going to omit the animation part, and the reason for that is because although animating these epochs make things more fancier and easier to look at, but it has nothing to do with real training essentially. So I'm just going to omit that. Now finally, so let me drink some water, I guess. Now let's train the. Okay, so let's define what happens at each and every epoch, right? So I'm just going to use D12 timer for giving a pretty picture, but okay, so let's omit that as well. Because it's not that necessary. But for metric, I'm just going to use the accumulator. So it's going to accumulate whatever number of metrics we're going to throw. So here we're going to use 3 metrics, which we will define later in this block. Batch size is going to be the x dot shape, which is of course the first dimension, which is the batch size, as we've seen in the slides previously. And Z is going to be, yeah, so basically Z is uh, the noise or noise vector essentially. So let me show you that. So these are Z, right? And Z maybe I don't know, it came from Z scores. So standard normal distribution utilizes Z scores. You can convert a normal distribution into a standard normal distribution using these scores.
Oh, Mrityunjay,
Yeah, yeah, yeah.
you forgot an underscore on line 16 in data iter.
916 and
The
data.
two words are separated. Like data.
Data and oh wow. Thank you so much. Yeah. So dodge normal. These are the parameters. These are the size, the batch size, and the latent dimension, right? Which is 100 in this case, right? We will define it later, I guess. So with that, we have x's and the z's essentially. And finally, I'm just going to define metric, which is just going to be the outputs of your updates, which is update update D and update G. And yeah, so it's just the accumulation of all of those output. The reason why we are doing it so that we can pretty print all of these outputs in the end, essentially. Although it will be much more useful if we were to animate our epochs, but let's follow that exact same thing that we've been following for all of those previous sessions, right? So trainer D, and now let's define the update. G, it's going to take that standard normal noise vector, right? Okay, let's see. Right. So using these, we can essentially define our loss in the and final. Now, so basically, let's uh, show the losses. These are the loss, which is metric of 0 divided the total batch size, right? Because we're normalizing it, and we just going to take the outputs of the update G with, and then normalizing it with batch size. Right. Hmm. I will do the no, the move. See, let's see things with 5 minutes. So the loss, and then finally the or after a particular topic, we can just print the losses, right? Uh, yeah, I don't know. Okay, let's use this. We could also print it at using echo. Maybe we will do that eventually. I'm just going to take the first three outputs in the decimal point. Yeah, let's only use these tools. Right? We have a loss in the discriminated part as well as loss in the generative part. Now, let's start with pretty scared. Just, so let me try to run it as January. Okay. So the problem with the GANs is, of course, it's extremely heavy to train. So last time, I think I remember, I was trying to train VAEs. It took me 2 or 3 days, and as well as I tried to uh, train GANs, and it took me a lot of time, right?
Just curious, what is your runtime currently? Are you using GPU?
Yeah, I'm using
Ah,
GPU.
okay.
Even okay, so I don't know how collab works, how it will give you better GPUs when you are a good guy. I don't know, but it's taking a lot of time. Yeah, but basic idea is the same. So now that we have implemented train and we know how to update generator as well as the discriminator, the output is going to look something like this. So we did exactly as we've seen in the original DCGAN paper and the things that are already being mentioned in the theory part. So if we were to run it for a couple of hours or minutes, uh, it will look something like this. So it it doesn't look good at all. Oh, by the way, oh, so I stopped by the way. So you can really see me. Yeah. So basically, as you can see, it sort of looks like a Pokemon, but not that much. So like. This morning, I started training this DCGAN, right? And it is still going on. Uh, I'm not sure I could show it to you, but it still isn't able to convert. So that is exactly the problem that Pierre mentioned in his talk, essentially. Uh, it's the problem with training the GANs. So like one of the problems is mode collapse and non-convergence because it won't converge, and of course we have diminishing gradient problems. Now, mode collapse has already been a problem with generative models for quite some time. Fully Bayesian model gives you a much better chance uh, at stopping from mode collapsing, and the reason for that is because you are normalizing it, normalizing your entire space uh, with your normalizing constant in the end, in the uh, fully Bayesian model, right? So one way to alleviate the mode collapsing problem is, of course. So let me emphasize more what is mode collapse in the context of GANs, essentially. So, so basically, the idea in mode collapse is for some modalities, we are able to fool the discriminator, right? Like for example, as you can see, that a discriminator is learning at the same time with the generator, right? And eventually, we hope that they both converge, right? But the thing is, at a certain point of time, maybe we can kind of get into certain minima, right, in which we are able to fool the discriminator. But the output of the generator isn't going to be that good, right? It can also happen the other way around. The discriminator is the discriminator is able to perfectly judge the generator, right? Uh, and of course, it wasn't able to give much chance for generator to improve. So within each one of the scenarios that I have mentioned, you can see the fluctuations within your while you are trading. So that exactly what happened to me when I first when I started running the DCGAN, the one that we've implemented right now, and it is still getting fluctuate, but it is kind of giving you fine enough output. So let me try to show that. By the way, the session, the coding part is over with this, right? So as you can see, the loss, here the loss of the discriminator is the loss of the, right? It can go higher and higher in the start. That happens most of the time, right? But the loss of the discriminator going down, which is kind of nice. So eventually, after I don't know 100 epochs, you can do, or even better, like oh no, so this is for 20 epochs only, right? Uh, I was able to run it for 150 epochs. So let me try to show that as well. Meanwhile, I guess if anybody has any questions, and of course, finally, let me add this slide because I quite like it. So here are the frontiers of GANs. So like as you can see, like after 2014, after the original GAN paper, folks come a long way, right? And it's been apparent in the area of art, essentially, and I don't know, creative coding and visual goodness, I guess. But in practical sense, I've used GANs to generate missing data. But the problem with generating missing data using something like GAN is that GAN is very okay. So the data capacity of GAN is pretty poor. So what I mean by that, you need a lot of data for it to read. So since we wanted to elevate the scarcity of data using GANs, it doesn't work that way. But if you have scarcity of data in a particular, in of course, in the case of images, right? Maybe you can use GANs, right? But it's not going to work that way, essentially. So people don't tend to use that, and people. I've used probabilistic graphical models that tends to work out a lot more because once you've injected all the priors that is necessary in a particular domain that you're working with, it gets pretty easy for you to generate data because you have some good idea of where the data is associated. Another real world use case I've seen is in the fashion industry. So this is a really good example. Now maybe you can generate multiple different patterns for your customers. You can make patterns specifically for each and every individual using GANs. And of course, you can walk inside the latent space of GAN and actually control GAN essentially. So this was a really hard problem to solve until recently. I think in 2020 paper called GAN space, people are using they first essentially use they first essentially project and take a look at the activation space of your GAN. From that, it will extract most of the principal components using PCAs. And using PCAs, we can actually control the behavior of GAN, which was like actually before that, like to the best of my knowledge, was pretty hard to do. So yeah, so these are the frontiers of dance, and I like this came via Twitter 2 or 3 hours before. Right? So as you can see, like it can be 3D printing and a few GANs and clip, right? Dali and clip, as you say, is pretty popular these days. Finally, the reference. I really like this visualization by Dan Lab, which uh, actually gives you a pretty good overview. Okay, so let me stop that because it's going to eat most of my time. So as you can see, the loss in the distance is going down. The generator is going to keep going eventually. Then it will fall down. That what's happening. But yes, yeah. So this is what I wanted to show. So after each and every epoch, you can see the generator loss and as well as the tail divergence, right? I think there was this question why people are using tail divergence, not cross entropy. Maybe you can use, of course, you can use cross entropy. Another term that associated with it is and will make it move on. But the basic idea is the same. So you have this discriminator. This is the loss space of your latent space of data out the samples. Once we have those samples, we can put the real one as well as the fake one in the discriminator and take these outputs, these predictions essentially, and from that we can backpropagate the gradient which happens in the discriminatory loss and the generative outputs, and put all of those gradients inside the generator in order to improve it. That's what basically happens in GAN. GAN paper, the original GAN paper, a deep learning book is kind of a lingua franca for all of these stuff. Basically, the authors did a tremendous job at writing it essentially. So I've learned a great deal from this book. I would encourage you guys to look at it at your own leisure. Finally, the server paper of GANs. So I guess that's it. Maybe